Okay, so welcome everybody to today's Quasi-World. So our first speaker today is Stefan Wenger from the University of Fribourg, and he will tell us about integral currents and metric manifolds and applications to Poincaré inequalities. So please, Stefan.
Okay, thanks very much for the invitation. It's a great honor and pleasure to speak here. So I'm going to report on work in progress with Giuliano Basso from the MPI Bonn and my current PhD student, Marti. And I must say I'm a little bit nervous about giving this talk because those of who know me a little bit, they of course realize that Poincaré inequalities usually doesn't come up in my talks, and so it's, I guess, the first time I talk about something related to Poincaré inequalities. But yeah, so there will be a section when I'm not 100%. I'm not an expert on. Okay, so let's dive in, and I'm going to start with a first relatively vague question. And this is the following, if I can get my slides to move. Yes. So remember, so when we have a compact oriented Riemann manifold, then we can always, integrate differential forms on N. And of course, we have a Stokes theorem for sufficiently nice domains. Okay. And in some very vague sense, I would like to ask the questions, for what metric spaces, can we still make sense of a Stokes theorem? And in particular, what is this good for once we can make sense for it? Okay. And well, of course, in a metric space, you first have to ask, what do we mean by differential form? So what should be the substitutes? And actually, so from a little bit, of course, we have the analysis on metric spaces, right, where differentiable structures are discussed and developed. And on the other hand, we have geometric measure theory in Euclidean and metric spaces. And in geometric measure theory, there is a notion of current, which basically uses a substitute for differential forms. Exactly, and that's what we're gonna look at. Okay, so let me maybe just give a very quick plan of the talk. I'll first quickly say something about what is an integral current in Euclidean space and then in metric spaces. So the motivation for developing these theories was at the beginning Plato's problems of finding area minimizing surfaces with prescribed boundary, but nowadays, of course, they're used in a lot of different contexts as well. And then we're going to go back to our questions once we know what is an integral current, and in some sense, what is a differential form. And then we're going to look at the existence of top-dimensional integral currents in metric spaces that are homeomorphic to a manifold, and give a first very easy application in some sense. And then I'm going to shift gear completely, and I'll try to look at a more serious application in the analysis on metric spaces concerning Poincaré inequalities. There we have a very deep theorem of Semmes that says that certain metric manifolds have a Poincaré inequality, and I'd like to give a conceptually simple proof of this theorem using our main result, which was actually in the smooth setting. 1x is basically smooth Riemann manifold, was proposed by Gromov and is already in Semmes' long paper where he proves his theorem. And if I have time, I'll give some ideas of the proof of our main theorem, which in some sense is also, not so difficult and mostly uses Lipschitz maps, and integral currents only come in to play, as limits in some sense. Okay, so let's recall what is a current. So the basic idea is that any compact-oriented n-dimensional submanifold in Euclidean space gives rise to a functional on compactly supported differential n forms, and the volume of M can be written as an operator norm. So the soup of this functional applied to omegas with what is called the comass norm at most 1. And Stokes' theorem tells us that the functional induced by the boundary of M is basically just the boundary applied to the exterior derivative of the differential form, right? And so now the idea of the RAM and then Federer-Fleming was to say, okay, when you want to try to solve Plato's problem, so find an area minimizing surface with prescribed boundary, right? You could run the direct method of the calculus of variation and take a minimizing sequence of smooth submanifolds, say. But then, of course, you have the problem that, you might develop singularities, or that this doesn't converge at all, right? And their idea was to say, okay, we'll look at the submanifold as a functional on differential forms, and so then we're in the setting of functionals actually in dual Banach spaces, right? And then we have stuff like weak compactness. So a Federer-Fleming current of finite mass is simply a linear functional on the space of compactly supported differential forms that is continuous with respect to this co-mass norm on differential forms. So such an N current comes, of course, with a mass measure, which you should just think of in some sense the volume of this generalized surface, and the total mass is then just the mass measure of the whole of Rn. And inspired by the Stokes theorem that we have above here, we can try to define the boundary of a current simply in duality with differential forms. Okay, so this is not really, this is a very general kind of surface, and in general doesn't have anything to do with an n-dimensional submanifold or anything alike. So such currents can be supported on smaller dimensional sets or higher dimensional sets. So this is for solving Plato's problem, is not really the right thing. So we would like to have something that is a bit closer to n-dimensional submanifolds. And so what Federer and Fleming proposed or defined are the so-called integer rectifiable currents. And the idea is that above here in this functional, right, we don't really need M to be smooth, okay? So we can introduce singularities, and we can start maybe changing the orientation. And actually this integral still makes sense if we replace M by a countably n-rectifiable set, right? Of course, these don't have tangent spaces everywhere, but at least almost everywhere they have approximate tangent spaces. So we can still talk about an orientation. And that's actually what an integer rectifiable current is. It's just an n current or a functional of the following form. We take integration over a countably n-rectifiable set of a multiplicity function. So you want to basically allow 2 times or 3 times and the same piece of the surface, and then an orientation, so a measurable orientation of almost every approximate tangent plane. Yeah, so whenever you've got such a countably Hn rectifiable set, you can choose an orientation and the multiplicity, and that gives you a very general kind of n-dimensional surface, right? Okay, of course, you would like to make sense of somehow Stokes' theorem, right? And so we further restrict this class, and we call integral current an integer rectifiable current whose boundary, which was defined in duality with differential forms, is still integer rectifiable. Okay? So in practice, of course, this is not easy to check, right? Whether when you have a form like this, whether you can really, whether the boundary is integer rectifiable again. But there's a very deep theorem, the so-called boundary rectifiability theorem by Federer and Fleming, which says that basically you just have to check whether the boundary has finite mass. And as soon as the boundary has finite mass, it is actually, again, an integer rectifiable current. Okay? So simple examples that you should keep in mind. And if everything is a bit too quick now, just think, first of compact oriented submanifolds, and then Lipschitz chains. But in the end, we will need in our setting something a little bit, more general, because in the setting we will talk about, Lipschitz chains are probably, could be always 0. Okay, so much to the Euclidean setting. And now what about metric spaces? So around 25 years ago or 30 years ago, De Giorgi wrote a beautiful short paper in which he proposed a definition of currents in the setting of metric spaces. And his idea was to replace differential forms, or use as substitutes of differential forms, tuples of Lipschitz functions. And the idea should be that such a tuple of Lipschitz functions should correspond to this differential form here whenever you're in Rn and everything is smooth. Okay. And Ambrosio and Kirchheim, they subsequently developed a beautiful theory of currents in a metric setting. And these are, again, in some sense, functionals, now not on differential forms, but these generalized differential forms. So the first argument f is a bounded Lipschitz functions, and the other are Lipschitz functions, should be linear in each argument, and they should satisfy some properties: a locality property, a continuity property, and a finite mass property. I'm not going to tell you what these are. I think it doesn't help too much, but maybe just a locality property. Okay, so the locality property should take into account that when a pi I is constant, then really the differential form d pi I should be 0, and so the current should evaluate this differential form to 0, right? So this means that's the locality property. So when pi I is constant on the support of f, then the t should send this to 0. Okay, and the finite mass property says somehow that if you evaluate t on such a differential form, then it should be bounded by the product of Lipschitz constant of the pi i's times the integral of the absolute value of a finite Borel measure, which is not which doesn't depend on f pi, on the pi i's. Okay, and the minimal such measure is called the mass measure. Think about it, it should be like the volume of your generalized surface, and that's a metric n current. Okay. Again, these are not really the objects we want here. They can be very far from n-dimensional surfaces in some sense. They can, for example, be supported on higher dimensional sets, but in the metric theory, not on lower dimensional sets. Okay, and now we can use the same ideas, duality with differential forms to, for example, define the boundary. Okay, so remember the boundary was defined in duality with differential form. So we take the exterior derivative. So what is the exterior derivative of this? This would just be df wedge d pi 1, etc. Right. So this corresponds to the tuple 1 comma f comma pi 1, etc. And that's how one defines the boundary of an n current. Okay. So in general, I forgot to say that in the Euclidean setting, it's already the case. In general, the boundary is not an n current anymore, okay? Because the finite mass property can fail. Okay, so for example, if you just integrate over a domain in R2 with a snowflake boundary, then the boundary should really be integration over this, but this evaluates to infinity. I mean, the mass is infinity. And similarly, we can define the push forward under a Lipschitz map. So in the Euclidean setting, this is again done by duality with differential form. So we would just take pullback differential form, but the pullback of such a differential form is really just, f composed phi, or phi composed f, and then d pi I composed phi, etc. Okay. And so if we have a current in X, then the push forward is again a current. Okay. And now integer rectifiable currents are defined almost exactly like in Euclidean setting. So, let me first maybe just mention this example here, the standard example. So if you take an L1 function, then you can define a current of finite mass in the sense of Ambrosio-Kirchheim simply by integrating here the multiplicity function times f times the determinant of d pi, where pi is just this function here. Okay, and of course, because it's Lipschitz, by Rademacher's theorem, it's differentiable almost everywhere. So this determinant here, this is a bounded measurable function. Okay, so now in analogy to the Euclidean integral on the integer rectifiable current, we make the same definition. Okay, so it's integration over a countably Hn rectifiable set of a multiplicity, which is integer valued, times, well, basically d pi paired with an orientation. So what is an orientation? Well, just think, you know, you have in some sense intrinsically, you have in some sense approximate tangent planes, but let me maybe just define it concretely quickly. So we can write sigma up to a negligible set as the countable disjoint union of bi-Lipschitz pieces of subsets of Rn. So on each of these subsets of Rn, you choose a measurable function that takes the value -1 and +1. And then you should think of integration here over the piece of the image, just as this integral over here. Okay. And of course, if you use the area formula, right, then this integral here is the integral over the image of, well, tau tilde composed phi inverse times these two functions here, times the determinant here divided by the Jacobian. Okay, so in some sense, this expression here is simply, in some sense, ±1, the determinant divided by the Jacobian. Okay, but you know, I would just like you to think of an integer rectifiable current as a countably Hn rectifiable set. You take a measurable orientation and the multiplicity, and that's it. Okay. And then, of course, we would like to know, when does this have a boundary with finite measure of mass, and this are then the integral currents. Okay, and in general, of course, if you've got such a sigma, a tau, and a theta, then the question is, you know, when is it an integral current? Okay, so this is very briefly something about integral currents. And now we can go back to our question and make it a little bit more precise what I want to ask. And right, every closed oriented n-dimensional Riemannian manifold, we have this integral current, which is just done by integration of differential forms. This is a cycle, so the boundary is 0. The mass measure is exactly equal to Hausdorff measure, or the Riemannian volume. And this functional is in some sense a fundamental, defines a fundamental class. And now the question is, well, for which metric spaces do we have kind of an analogous object? So we can say, okay, for which metric spaces do we have an integral current such that, for example, the mass is proportional to the Hausdorff measure and the support is the whole X. And the question is, of course, you know, why should we care? I mean, what does that help us, right? In some sense, we could think of this as something like allowing a Stokes theorem in a certain sense. But of course, we have, you know, our motivation, our applications. Okay, so let me give you our main theorem and then go over to the analysis on metric spaces. And here you already see the first assumption that we will have in our main theorem, which is something that is quite common in the analysis on metric spaces. This is linear local contractibility. So we call a metric space linearly locally contractible. I'll denote it by LLC, even though I know, of course, that very often stands for linearly locally connected. But for me, LLC is always going to be linearly locally contractible. So if balls of radius r can be contracted in balls of radius lambda times r for a fixed lambda. And then a second hypothesis we need is a bound on the Nagata dimension. So a metric space is said to have Nagata dimension at most n, if there exists a constant C, such that for every S, we have a covering of our metric space by sets whose diameters are always bounded by C times S, and such that any set of diameter S, here denoted in red, meets at most n+1 members of this covering. Okay. So maybe, so this Nagata dimension very often comes up in considerations of Lipschitz extensions and things like that. Let me maybe just make a few remarks and give some examples. So any geodesic two-dimensional metric surface has Nagata dimension 2. Then the topological dimension is always smaller or equal to the Nagata dimension. And the Nagata dimension is always smaller or equal to the Aswad dimension. This was shown by Le Donne and Raiola. And in particular, when X is doubling, then the Nagata dimension is finite. And when X is Ahlfors n regular, then the Nagata dimension is at most n. So Nagata dimension is preserved under quasi-symmetries. And an interesting construction that sometimes comes up also in analysis on metric spaces is if you take a metric space and you take a ball and you collapse all the points of this ball to one point, and you consider the resulting metric space with the quotient metric, then the Nagata dimension stays the same, or is no bigger, right? Whereas, for example, the Aswad dimension can explode, right? And for example, also, the Ahlfors regularity under this construction it might not hold anymore. Okay, so for example, if you take Euclidean space, the Euclidean 2 plane, you take a disk, you collapse it, then this is not Ahlfors 2 regular. So some decomposition spaces, probably you can bound to the Nagata dimension. Okay, so now our main theorem about the existence of integral currents. I will call metric n manifold a metric space which is homomorphic to a closed, smooth, orientable n-dimensional manifold. Okay, so I know this is not really, what's usually the term. So usually it is just a topological, orientable n-dimensional manifold. I'll just take this term. Okay, smoothness will probably we don't need quite that. We actually only need that we have that's a Lipschitz manifold. Okay, so when you have outside dimension 4, then we can actually replace the smooth by a topological manifold. And closed, I think we can also get rid of closed, but I'll just stick to this at the moment. And then our main theorem is the following. Okay, so let X be a metric n manifold. And so the topological dimension is n, so the Nagata dimension is at least n, and we require that it's actually equal to n, and it has finite Hausdorff measure. Then if X is linearly locally contractible, then we have an integral cycle whose mass is proportional to the Hausdorff measure, and in particular, and moreover, that the mass measure of R balls is at least Euclidean. Okay, so in particular, the support of the measure, right, is the whole X. Okay, so that's in some sense you would like to think as of this T as like an analytic fundamental class of our space X, right? So I'll discuss this a little bit later. Linear local contractibility, for example, in dimension 2, we don't actually need this. Okay, so we can still construct an integral cycle, but of course, in general, this will not have the lower bound anymore. Okay, so in general, the Hausdorff measure is strictly bigger. So yeah, okay. And one immediate corollary is, well, because integral currents, they live on countably Hn rectifiable sets, right? So we actually obtain that space X, as in the theorem, is countably Hn rectifiable. Okay, so this doesn't follow for the specialists. This doesn't follow from the fact that the support is a whole X, because in some sense the Hn rectifiable set is just dense in there, but we also need this lower bound here. Okay, so that's a first little application. Okay, any questions so far? Okay, then now let's change gears completely, and let's go over to analysis, to some applications in analysis on metric spaces. And you're, of course, most of you are much more expert on this topic than me. So yeah, let's just recall for those who haven't seen it on what is an upper gradient. So let's fix a function u, and then a Borel function g with values in 0, infinities in upper gradient if we have this inequality for every rectifiable curve. So for smooth functions, right, on Rn, then of course just the norm of the gradient is an upper gradient. And so what you should really think of as an upper gradient is something, a substitute of the norm of a gradient. Okay. So, and of course, in general, in a general metric space, there's not a lot of relation between an upper gradient and the function u, right? For example, if this condition is empty, if you don't have any rectifiable curves in your metric space, okay? But once you add some assumption, then it gives you a lot of tools, and one of these assumptions that has played a big role in developing first-order calculus in the setting of metric spaces is that of a weak Poincaré inequality, which is presented here. So a metric measure space is said to have a weak Poincaré inequality if the averaged integral over every ball of, well, u minus the average of u on b is bounded by the diameter times this averaged integral of the upper gradient for every function upper gradient pair u and g. And of course, by Hölder's inequality, if you have a p Poincaré inequality, then you also have a q Poincaré inequality for every q bigger. So the smaller you make p, the stronger this becomes. Okay. And so doubling metric measure spaces with a Poincaré inequality, they're usually called PI spaces. They have very good properties, and a lot of first order calculus has been developed on such spaces, and also a lot of tools or a big theory of quasi-conformal and quasi-symmetric mappings have been developed on there. So a few properties. I'm not going to mention many names. I think I could extend this list, indefinitely, because there's been so many results on PI spaces. But let me just mention a few. So PI spaces, they're always quasi-convex. So for me, it's always going to be a complete doubling metric measure space, right? And they have what is called a measurable differentiable structure. And these results go back to Cheeger. And then you have various notions of Sobolev spaces on metric measure spaces. They're equivalent on PI spaces. Then Lipschitz functions are dense in the Newton-Sobolev space. Poincaré inequality is stable under measured Gromov-Hausdorff convergence. And the Poincaré inequality is self-improving. That's a big theorem of Keith and Zhang. And I could, continue a lot if I don't mention some of the results of people. I apologize. I'm sorry. You see, this is the part where I'm definitely not an expert. Okay. So, of course, the question is, what kind of spaces support such a Poincaré inequality, right? Are there a lot, or are there only a few? Well, no, there are a lot, and they come from different sources. One has Euclidean spaces, compact Riemann manifolds with lower bound on Ricci curvature, and also their limits. They were studied by Cheeger-Colding a lot. Then metric measure spaces with synthetic Ricci curvature bound. I think that's by Tapio-Rai a lot. Then sub-Riemann manifolds, boundary of certain hyperbolic groups, and so on and so on. Okay, and one theorem which gives also a big class of metric spaces that have been studied a lot in analysis on metric spaces is the following theorem, a deep theorem by Semmes in 150-page paper, is that a metric n manifold, which is Ahlfors n regular and linearly locally contractible, supports a weak one-Poincaré inequality. Okay, so the theorem is actually stronger than this, but I'll just I'll stick to this. And I would like to convince you that our main result can be used to give a relatively easy proof of this theorem. Okay, and this theorem actually in the smooth setting, when X is a smooth Riemann manifold, was proposed by Gromov. And there's already a remark, like a one-page remark in Semmes' papers toward the end, where he briefly describes this idea of Gromov in the smooth setting. Okay, so we will not actually prove a Poincaré inequality directly, but a relative isoprometric inequality, and this is known to imply a Poincaré inequality. So we say that the metric measure space has the strong relative isoprometric inequality if for every Borel set and every ball, the minimum of the two measures here is bounded by the diameter times the outer lower Minkowski content of E in a bigger ball. Okay, so and what is the outer lower Minkowski content? You basically you blow up your set a little bit. Okay, so you take the H neighborhood for small h, and then you look, at in some sense the annulus, the measure in the annulus, and you take that divided by h, and you let h go to 0. And a theorem of Bobkov and Federer from the 97 says that whenever you have a complete doubling metric measure space, which has the strong relative isoprometric inequality, supports a weak one-Poincaré inequality. Okay, and basically what you use is something like a co-area inequality, where you take integrals over the level sets of functions, and so it's not so difficult to prove this. Okay, so when we want to give a proof of Semmes' theorem, then it suffices to just prove a strong relative isoprometric inequality. Okay, so let's try to do that. So we start with the Borel set, and I'll just, denote the Hausdorff measure by mu, so that mu plus, is a bit nicer to write than Hn plus. And what we're going to prove is actually this Euclidean isoprometric inequality here. Okay, so this is in some sense what you get in Euclidean space is this exponent here. And this actually implies the strong relative isoprometric inequality, as you can see easily, with just using the Ahlfors regularity. And right here, we don't have any diameter in there anymore, but that just comes out with the measure. Okay, so I will suppose assume for simplicity that E is actually completely contained in the ball. Okay, the general case is a little bit hard, or not harder. It's a more technical, but the idea is exactly the same. Okay. And I assume that the diameter is not too big, because if the diameter is big, right, we can actually not have this. Okay. Okay. So then, of course, without loss of generality, we can assume that the Minkowski content is not too big, because otherwise, it's anyway trivial. Now, let me try to just give one picture, okay, and explain for a little while this picture. Okay, so we take our space X and we embed it into an I space isometrically, like L infinity, or later we're going to take the injective hull. And here we have our X. This is just this black line here, right? And now we have our set E, our Borel set E. We would like to restrict our fundamental cycle here, T, which we have from our main theorem. We would like to restrict it to E, but this is in general not an integral current. But if we take the H neighborhood for almost every H, this restriction here is actually an integral current. We look at the boundary of this integral current. This is an integral n-1 current in X, okay? And now what we would like to do, we would like to solve Plato's problem in L infinity for this for this boundary. Okay, and in L infinity you can do that. You can solve Plato's problem. So you find a mass minimizing n current, which is here my S, which is just straight, which is not in X anymore, but it is outside, right? And this has good properties. It satisfies in L infinity, we have a Euclideanized parametric inequality, which, you know, just basically to say almost the same here, except you have the mass of the filling, you know, and the mass of the boundary. And another property is that when you have a ball centered on a minimizer, which doesn't touch the boundary of the minimizer, so it's like this green ball here, then the mass is at least r to the dimension, so r to the n, okay? So now what do? Now we use the linear local contractibility to construct a Lipschitz mapping, not to X, but in a very small neighborhood of X, right? This we can do. We can do actually continuous retraction onto X, but we would like to have Lipschitz because we would like to push forward, you know, the current, that we cannot do it under a continuous mapping. So we go near X, right? And because of the linear local contractibility, we can construct this retraction or almost retraction in such a way that the image is in, well, if we take balls here, it's in the image of, you know, somewhat bigger balls, okay? And the covering that we take of our minimizer here is by balls whose radius is basically proportional to the distance to the boundary, to this boundary here, right? And, you know, we don't want to have too much overlap, okay? So then the picture looks basically like this. So what does that help us now? Well, now we push it to M with, well, a Lipschitz approximation of the homeomorphism between X and M, okay? And so then, well, we get basically an integral cycle. So if you take the red one and the blue one, so that's this difference here. If you push that forward, this is an integral cycle in M, okay? But in M, we know that every integral cycle is just a constant multiple of the fundamental class. And if the ball was small enough, this, you know, this integral cycle here cannot cover the whole of M, okay? So it must be 0. And since it is 0, and we have here an approximation of the homeomorphism, we can conclude that, you know, this current T restricted to EH, and thus EH itself, the set itself, has to be in the union of these balls, okay? And the sum of the radii to the n, we can basically bound from above by the mass of S. Okay, so that's the basic idea. Okay, and now in the last 10 minutes, I will just I'll make this a bit more explicit. So let's start. Well, there exists arbitrarily small h, such that the mass of the boundary of this current is bounded by the lower Minkowski content. Okay, so this is just this is what is called a slicing inequality. So it's basically co-area inequality you apply under the definition. Okay, and now take y as either a little n infinity or the injective hull. So basically, you can take L infinity. Injective hull is good because it's still compact when X is compact. Okay, so but don't worry about this. Okay, so then we have a mass minimizing filling. This is yeah, that's because this is an I space. One can prove this, and any such mass minimizing filling satisfies the Euclideanized parametric inequality. That was proved by Gromov in finite dimensional setting, and then by Ambrosio-Kirchheim in L infinity, and it follows from my thesis that in injective metric spaces is also the same. And any such minimizer has this property that I already said, that balls that don't touch the boundary and which are centered on the mass minimizer, they have at least Euclidean growth. Okay, and in particular, the support of S, so that's the support of the measure of S, cannot be too far from the support of the boundary, because otherwise you have too much mass, right? Okay, so that means this S is actually, you know, relatively close to X. And now we cover, as I said, we first cover the boundary of S. This has Hausdorff n measure 0, so we can cover it by finitely many balls, such that this sum is extremely small. And then we can choose finitely many points in the support of S without the boundary, such that, well, these balls don't touch the boundary. Okay, so here we have the distance function to the boundary times a constant which is between 0 and 1, right? So they all have the mass growth of this, or the mass of this is at least, you know, r to the n, and such that when you blow them up a little bit by a constant which only depends on the data, then actually the whole support is in there. Okay. And then what we get for the sum of these r to the n's is bounded by the mass, because the multiplicity is bounded, and this is bounded by the lower Minkowski content to the right thing. And now we take this almost retraction, so a Lipschitz map, which takes a neighborhood of X to a very, very small neighborhood of X with this property here. This comes just from the linear local contractibility. And then this property here implies immediately that the image of the support of S is in the union of these balls for suitable centers, where basically the radii are just a little bit bigger. Okay. And now we look, as in the picture, at this cycle here. So this is a cycle in Y. Its support is very close to X, and then we send it over to M with a Lipschitz approximation of the homeomorphism, right? And there it has to be equal to 0, because it's a constant multiple of the fundamental class, so this integral current defined by integration, but it doesn't have, you know, it doesn't cover, the support is not the whole of M, so it has to be 0. And then you can, in some sense, pull this back, or you deduce that, you know, this current here has to be very close to this current here. So in other words, this set E is in a small neighborhood of the support of this push forward, which we know what it is. And then you get, simply using the Ahlfors regularity, you get the inequality that we want. Okay. So this is a proof of Semmes' theorem. Okay, and of course, right, where did we use our main theorem? We basically used it, well, if you restrict, if you take a subset, even a nice subset of X, we have to look at its boundary, and we have to somehow, you know, say that this is an n-1 cycle. And then we have to use Plato's solution of Plato's problem, right? We want to have a minimizer. And if we don't know that this in some sense is a current, we can't use the isochromatic inequality, and we don't know what is a minimal filling, how to do that. So in the smooth setting, of course, right, you can just take a smooth domain, and then because you have a fundamental class, then, you know, this smooth set is an integral current, and you don't actually need you don't need our theorem. But in the setting where you don't know whether a current exists, then you need this. Yeah. Okay, I think, do I have five minutes?
Yeah. You do.
Yes, good. Okay, so are there any questions? If not, I'll just very briefly explain a few ideas, and the ideas are not so difficult, and you don't not need to know a lot about currents. Okay, so that's again the theorem that we would, but the main theorem that we would like to prove. And just for simplicity, we will assume that X is quasi-convex. That just makes the statement a bit nicer of what I'm going to say now, but you actually don't need it. And we take again the injective hull of X. If you want to think, just take L infinity. Okay. So then in the first step, we have a factorization theorem, which tells us that there exists for every R a simplicial complex, actually a finite simplicial complex, and equipped with a geodesic metric, such that every simplex has side length R. And we have a Lipschitz map from X into this simplicial complex, and from the simplicial complex into the injective hull, such that both are have a uniform Lipschitz bound, and the phi r is so the composition of psi r with phi r is close to the identity. Okay, so now we take a homeomorphism from M to X. And now we take the composition of rho, the homeomorphism with psi r. This is, of course, only a continuous map. So if we take the fundamental class of M, we cannot push it forward by this map because it's only continuous. So what we do is we just take a Lipschitz approximation of this composition here. Okay, this exists because a finite simplicial complex is locally Lipschitz connected. Okay, so we can always approximate continuous mappings by Lipschitz mappings. And then we simply define a current in the simplicial complex as a push forward of the fundamental class. Okay, and if you take another Lipschitz mapping that is close by, then the two are homotopic, and so Lipschitz homotopic. And that means, you know, if you take the two currents, they have to be actually the boundary of a higher dimensional current, right? But there are no higher dimensional current in our simplicial complex because the dimension is n, right? So that means this SR is actually independent of the choice. Okay. So now the fundamental proposition that we have to prove is that this mass of SR is uniformly bounded, so independent of R. Okay, so let's just accept this for a moment, and I think I will not be able to prove it, and then we can more or less relatively quickly get the existence of our T. So now we push this SR forward by our map phi R that goes into the injective hull. You know, this is going to be close to X, right? It has uniformly bounded mass. So we can use what is called compactness and closure theorems to say that there exists a sequence or a subsequence which converges weakly to an integral current. And, you know, because all these integral currents are closer and closer to X, the limit current has to be actually a current in X. Okay. And now why is this not zero? Of course, in some sense, it could be zero, but we can just push it forward via a Lipschitz map, which is close to the to the homeomorphism, the inverse of the homeomorphism, and then this composition is close to the identity, and so Lipschitz close. So that means for sufficiently large J, we have that the push forward has to be the fundamental class of M. So the push forward under T has to have the same property, and from this it easily follows that the support has to be the whole X. Okay. And now we get a lower bound, and this is very similar to the proof of the relative isoperimetric inequality. We basically just want to show that the mass of the boundary is relatively big, okay? So the restriction to a ball, and if this is not the case, we take again a minimal filling, we push it with this pi, and this has to, if it's very small, it actually has to be in some sense in the annulus. Okay, and then you compare it with M again, and you get the contradiction. Okay, and then you have this, and so that means we get this lower bound, and from this, of course, it also follows that the mass measure is bigger or equal constant times the Hausdorff measure. And then the upper bound is basically just a proposition that we have, but localized. And the proposition, is actually, is surprisingly involved. I'm not sure whether there's So there we need, unfortunately, The problem is, what is the problem? So we have a continuous map, and if we approximate it by Lipschitz map, we cannot bound the Lipschitz constant. And usually the mass of the push forward, right, is bounded by the Lipschitz constant to the power n times the mass of the current. And so there we don't get anything, right? So we can't do this directly. But I think I'll just stop here. And if you have questions, please let me know.
Yeah, thanks a lot, Stefan. Yeah, so let me open the discussion. Are there any comments or questions? Well, let me ask a question. Can you go back to your main theorem, please?
Mm-hmm.
So you said, I mean, a consequence of your theorem is the one Poincaré inequality, right? Suppose you already assume that you have a Poincaré inequality. Is it then much easier to get your fundamental class? I mean, using, for example, Cheeger's theory? Yeah,
that's to be honest, I don't know how. Even if I know that the X is countably Hn rectifiable, or even uniformly rectifiable, I just don't know how I can construct a good orientation, right? I mean, I have all these Lipschitz pieces or bi-Lipschitz pieces, but they can be extremely wild, right? And I don't know how to put an orientation on them easily. Okay, it makes the proof of this proposition of the upper bound a lot easier, because we actually need Bates' pure unrectifiability theorem, because we don't know. We just know that we don't really. There could be lots of purely unrectifiable part. And if we know that this goes in with our maps into the simplicial complex to a negligible set, then we can bound the degree of our mapping. Okay, and so if we have rectifiability, then this part would become easier. Okay. But I'm actually not sure whether one needs all this stuff to prove that the degree is bounded. So once we have the degrees bounded, then you can get the upper bound relatively quickly. But yeah, the answer to your question is I don't know how one can use even uniform rectifiability to get a current without boundary, or even with boundary finite mass. I have no clue how one could go about it.
I mean, as you mentioned in your talk, Semmes actually proves a stronger result, right? If I remember it right, he constructs this kind of pencil of curves between any 2 points, which then implies a one Poincaré inequality. But I guess, I mean, you can't get this from these methods here, right? Because
no, unfortunately not. I mean, we can't. I mean, at the moment, I don't even know how one could say, for example. For example, if the Nagata dimension is higher, or if the linear local contractibility, is weakened to this geometric contractibility function. I don't know how to do it. Okay, well, so and yeah, it's true. I mean, so one really needs the Ahlfors regularity. Okay, at some point, in an equality, if you don't have the upper bound, the upper growth bound, then it just fails. So yes, that's true. That's a weak point. We don't get the full theorem.
Well, I mean, of course, Semmes's paper is extremely long and technical, right? As you said, I mean, it's what, more than 100 pages, I think.
Yeah, 150.
If I remember it right, he also uses this kind of idea of using a simplicial complex, right?
Yes, so this is very similar. This is very similar, exactly. So that's that. And actually, I was surprised because I didn't really know this until we started working on this. And of course, we were using these simplicial complexes, right? They come basically from techniques of Lang-Schlichenmeyer with Lipschitz extensions. And then I looked at Semmes' paper and thought, oh wow, a lot of things there, are in a more general setting and a little bit similar setting. They're actually there with these maps, but you can just not. Yeah, that's one problem. We tried to use, his constructions. But the problem is then, the Lipschitz constants are of course not bounded. Okay, the smaller the scale, you can still get the same dimension of the simplicial complex, but the Lipschitz constants they just blow up, and then we can't do anything for our currents because that's really what we need. This uniform bound, the Lipschitz constant.
Yeah. Okay. Thanks for these comments. Any other comments or questions?
Yeah, I meant to ask, was proving or reproving Semmes' theorem a main motivation to try to prove the statement you got, or were you just mostly aiming at finding an equivalent for statements that were known in spaces with more structure and then happened to find out that you can prove stuff like Semmes?
Yes, okay, that's a good question. So yeah, one main motivation was definitely Semmes' theorem, but also, in recent years, when people started looking at distances between metric spaces and not where the Gromov-Hausdorff distance is not good. For example, if you have sequences of Riemann manifolds with a bound on the scalar curvature. So in general, if you have a sequence, like say of spheres with bounded scalar curvature, then you can't find any subsequence which converges in the Gromov-Hausdorff sense. You can have hairs growing out and things like that. And that was a motivation for Christina Romani and myself to find something what we call the intrinsic flat distance, where basically you look at Riemann manifolds as integral currents. You embed them a little bit like Gromov into a common metric space, and then you don't take the Gromov-Hausdorff distance, but the Hausdorff distance, but you use basically the flat distance between them. Basically, you look at the smallest mass of a current whose boundary is the difference of the two. And so we called these things integral current spaces. Okay, so basically a metric space with an integral current on it that has certain properties. And so yeah, one basic question is which metric spaces arise as these current spaces. And that was a little bit for me a side motivation because there's not lots except Riemann manifolds and limits of those. And so I always thought that's a natural, these are natural candidates. Yeah.
So we have time for one more quick question. Dimitrios.
Hi, Stefan. Thank you for your talk. I'm mostly interested in dimension 2. And you had the result that holds even without the LLC assumption, the upper inequality. So the question is, does this reveal anything about the geometry of the space? Meaning, we're interested in identifying, for example, the locations of the space that arise by collapsing a ball to a point, for example. How does this information is conveyed in the integral current in dimension 2?
That's a good question. I mean, there, the result in dimension 2, of course, in some sense, just follows from the weak quasi-conformal parametrization, right? So, if you have a Sobolev map, then this induces an integral current, and the integral current comes just as this. So I think when going to integral currents there, you actually lose information, right? So I think, a parametrization, I think, will have probably more information than what you get out there. Of course, you can do in some sense the same proof in dimension 2 and just look at sequences of integral currents instead of sequences of Lipschitz mappings with bounded energy. But I don't know, but I doubt that you get more information or something additional. Yeah, so yeah.
Okay, thank you.
Yeah, so we are running out of time here. So let's thank Stefan again.